here we are with Simon Clarendon, who's a researcher with New South Wales DPI, and he's with the Soil and Water Unit, as Luke and I are, and he's located in Tamworth. Simon has a background in nutrient management, in particular the mitigation of phosphorus loss from agricultural landscapes, and he's previously presented that information and that work in previous SNOC webinars. So currently Simon's working on a variety of projects ranging from work in New South Wales, from the south coast of New South Wales for the clean coastal catchments, which people may be aware of, to projects out in the Western Division in New South Wales for the Rangelands Living Skin project.
Thanks for the introduction, Abby. So we were asked if we could do a presentation on potassium, and so this is a broad overview. Some of you might already know the stuff, some might find some new stuff, or it might be a good refresher. I suppose it's more about promoting discussion around potassium and its importance. So potassium, and plants, why is it so important? So it's important for ATP production, protein starch, and enzyme activation for ATP production for photosynthesis. It heavily assists in the control of the opening and closing of stomata on the leaves, which regulates the oxygen, carbon dioxide, and water vapor. It lowers the osmotic water potential in the cells and increases the ability of water to uptake by roots. It increases root growth and improves drought resilience. Interestingly, it can take up luxury amounts of K when available in the soil, so that means it's above the requirements of the plant for growth. But also you can have deficiency and you can get stunted plant growth, which equals a reduced yield. Noting too that potassium is only taken up in its ionic form. So looking at just putting potassium in the context of the wider environment. So when we talk about nitrogen and phosphorus, we know that can cause eutrophication of waterways and have flow-on issues. So unlike nitrogen, there's no gaseous losses. So in that way, it's more like phosphorus. It's not considered an environmental issue due to the fact that it doesn't cause things like eutrophication, but it can be an agronomic issue. You can have too little or too much. Too little and you get obviously yield reductions. Too much, and in the situation where you get good season, high rainfall, or animals going straight onto it, you can get grass tetany. So usually when you look at a fertilizer packet, it has in nitrogen, phosphorus, and potassium. It's one of the big three. So it's obviously very important in plant growth. However, let's change that around and put it in terms of the dynamicity of potassium. So when I'm talking about that, I'm talking about its pathways. Nitrogen is very dynamic, so there's a lot of lost pathways or changes. In phosphorus, there's less so. So for example, in phosphorus, if it binds to a site, like a high iron site, the longer it's there, the harder it is for it to be released, whereas potassium sits somewhere in the middle, so it can slowly release over time, even from the mineral pools. Potassium is absorbed by plants in the second largest amount behind nitrogen. So potassium cycling. The yellow outline circles the readily available potassium. So if you look at that somewhat messy diagram, we can see that the soil solution pool of potassium is where the plants take it up from. You then have the surface absorbed potassium. So that's looking at things like organic matter, surface, planar surface on clays, as well as iron and aluminium oxide surfaces. So those two pools are more the readily available pools. That's about 2% of your total potassium in your soil. You then have all the other layers, which are all to do with the clay types and clay minerals. Some are slower than others. For example, the structural potassium in feldspars, it will eventually go into soil solution, but it's a slow weathering process over time. We can see if you import hay, you'll get a large amount of potassium in the hay, in the plant material, potentially because you're taking more potassium off-site than you are putting back into the soil. Then sometimes you'll have to fertilize to be able to get the soil solution potassium for plant growth. Importantly too, when you start to introduce animals, urine and dung are very important. So the main drivers of potassium cycling, clearly mineralogy and particularly mineralogy of clays, and also moisture, with the moisture to be able to take it up by plants. You also have source of dead plant material layering in the top layers and then slowly leaching down once binding sites are saturated. Just back to the cow image back, if you look at potassium percentage of total intake by a cow in dairy, you can see the majority of it, probably about 70%, is urine. So you're depositing a lot of potassium back in the soil in a concentrated spot. So it's important to include that when you're doing nutrient budgets and wanting to apply more. So removal and losses of potassium, you get product removal off-site. Also, erosion should be considered. So that's any of those pools that we saw earlier on of potassium, they can be eroded off the landscape. So it's important to account for erosion, and that obviously erosion is how much rainfall as well as soil type, slope. Leaching, so binding sites for potassium, much like phosphorus, can saturate depending on the soil type, so it can move down the profile. So for a sandy soil, you'd expect that like phosphorus potassium will leach both horizontally as well as vertically, obviously horizontally depending on the slope, vertically as well. So the potassium, it can move down the profile and you'll get that more in sandy soils. But in clay soils, you have macropores, and that can be a considerable movement of potassium down below the root zone. So it's leaching is soil type and rainfall dependent predominantly. Depending on the clay type will depend on its capacity to hold potassium. There might be some more learned people out there that know more about potassium and soil test in the cropping space, but for pastures, we can see that some work's been done over the years, and we've got some nutrient response, critical value response curves for potassium, and it's been separated out into different soil textures. So we can see that obviously a sand's going to have a lower critical value because it doesn't have the same capacity to hold on to it as opposed to a clay loam. You can see also in the drawing there on the map that was done accounting for nutrients project, we can see that some paddocks have got abundance and some paddocks don't have enough. So it pays to soil test. Co-LK is utilised as an efficient way if you're already doing co-LP. However, there is a strong linear relationship, and I noticed Cameron Gooley's online, he might be able to tell me the number again, but if you measure exchangeable K in the CEC measure, there's a multiplier and you can actually get co-LK. Utilising that information, I just wanted to, where does potassium sit if you measured a lot of soil tests, a lot of farms? So the whole farm nutrient mapping in Western Australia, undertaken by David Weaver at DPIRD and a few others. Basically, they've had this project where they've been soil testing on different properties around the southwest of WA for about 12, 13 years. And of all those, utilising the curves that Cameron Gooley's formulated, 60% of the tests are above and about 40% are below the critical value for K. So that shows that potentially we could see an improvement in production. Dave Weaver also noticed that high rainfall in 2021, largely sandy soils, they had a greater K efficiency going into 2022. So that just again reiterates leaching on sandy soils. So I just wanted to point out quickly that potassium accumulation, or in this case soybeans in plants, changes over time, and we can see that there's a maximum rate at a point. So, if we don't have enough for that plant growth, do we need a foliar application during the season to reach plant requirements, alongside having already soil tested and put on what's required. So in brief, potassium is very important for plant function. Potassium levels low, you're not utilising other nutrients well. It's that Lieb's law. If we go back a few slides to where we've got the barrel on the right, if potassium is the limiting factor, then obviously we're not maximising P and N use or other nutrients. Environmentally sensitive areas where phosphorus and nitrogen will be more leaky, getting potassium right to improve plant growth may reduce losses of nitrogen and phosphorus because it's been put into the plant rather than just sitting in the soil and being available to lose. Account for redistribution of potassium in nutrient budgets. So specifically, I wanted to point out that in a pasture situation, urine and dung, we can see that mineralogy, specifically clay types, are the key driver of potassium cycling. And the 4 R's apply to potassium when it comes to fertiliser management. And I'd just like to acknowledge Cameron Gooley, Dave Weaver and Nathan Robinson helping me put this together. And a lot of my reading came from improving potassium recommendations for agricultural crops. Came out last year. It's an open source and it has some very good information in it, and also another website that may be helpful.
Is it an interaction between organic matter in the manure and all the K that's in the manure, and that's what helps it hold in those lighter soils?
So the question is, I guess, referring to the map that we've got in front of us right now again, why would certain soils have such high potassium levels? And Simon alluded to the fact that the supply capability of animals, where the potassium use efficiency is around about less than 10% usually. So that means 90% of all the potassium that the animals are eating is actually coming out in urine and dung. And so you've got this very high concentration of potassium, and if you've got enough of that feeding into the system, then the potassium is going to exchange other cations off the exchange sites and become a real source or a dominant source of cation at a much higher proportion than it would be in these other paddocks. So it's all about that supply of potassium displacing other cations off the exchange sites and being such a dominant part of the picture. I mean, bearing in mind that calcium in particular will always be or expected to always be the highest cation.
The highest. And that nutrient redistribution, if you like, on farms is a particular issue in dairy farms because of that night paddock moving animals around stuff.
Yeah, it certainly is, but the same principle applies if you've got concentrated areas like stock camps for both cattle and sheep.
Yeah.
So you'll have the same sort of thing. You find the same trends. Animals tend to congregate on the slopes and up slope, so you'll have higher concentrations of potassium upslope than you will have on the side of the slopes. So, you know, the animals do actually, because of that very low potassium use efficiency, they have a big impact on the distribution patterns of potassium. And then the other factor, of course, that's been touched on is the soil's potential to retain that potassium. You've got these white sandy soils in Western Australia, for example, that have a very low cation exchange capacity. You're going to have a very low amount of potassium that the plant's going to have access to.